We're given a nice data table and graph showing R of t, which represents the rate of fuel consumption. And so the first question is asking about R prime 45. And the first thing that I want to recognize is that the units of R of t are gallons per minute. So if we do the rate of change of R, it's going to have to be gallons per minute per minute. So the first thing I'm going to write is gallons per minute squared, because there are some times where I can get 1 point for just having the correct units. So I want to do that. I want to get that down first to make sure I get that point. So then to approximate R prime 45, we have to use this table. And we're going to do the average rate of change using this table on an interval that contains 45. So 45 falls between 40 and 50. So the instantaneous rate of change at 45 is going to be approximately equal to the average rate of change between 40 and 50. So I have to use my average rate of change formula. R prime 45 is approximately equal to, we're going to do R of 50 minus R of 40 over 50 minus 40. Okay, so then R of 50 is equal to 55. So we have 55 minus R of 40 is equal to 40. And then that's going to be over 10, which is 15 over 10. So we could reduce that, but since this is an FRQ, we don't have to. We can just leave it as 15 over 10 gallons per minute squared. Okay, part B is asking about this R double prime 45. So it says the rate of fuel consumption is increasing fastest at t equals 45. So what that language needs to tell me is that R prime t is at a max at t equals 45, because that's where R is increasing fastest. That's where its slope is largest. So then what does that tell me? Okay, this implies that R double prime 45 equals 0, right? Because R prime is going to be at a max when R double prime is equal to 0. So we can use that language to reason that R double prime 45 must be equal to 0. So next it's asking for a left Riemann sum from 0 to 90. And you could use the graph if you want to talk about the left Riemann sum, but we need to use the precise values from this table. So we're going to take a pair of two values. And this is tricky because it's vertical and we're talking about a left versus a right. But we can just use the top value, right? It's going to be this. It's going to be. I mean, you know that 0 falls left of 30 on the number line, so we would use 20 if we pair up 0 and 30. So we're going to use the difference between 0 and 30 is 30 times the left y value is 20 plus. Okay, now we'll go 30 to 40. Okay, that difference is a difference of 10. Okay, and then we're going to multiply by 30. Okay, plus, okay, now we're going to go 40 to 50, and that's also a difference of 10, and then we're going to multiply by 40, the left of the two y values. Okay, plus 50 to 70 is 20, and we're going to multiply that by 55, and then finally plus 70 to 90 is also 20, and then we're going to use 65 if we're doing a left Riemann sum. Luckily, this is calculator allowed, so you can just type this long expression into your calculator, and you're going to get 3,700. And that's 3,700 gallons, because it's the integral of R of t, which is gallons per minute. Now, is this an over or under approximation? That's where it's helpful to go to the actual picture now. So there's our first rectangle that has a base of 30 and a height of 20. And then our next one is going from 30 to 40. We're going to use the left y value from 30 to 40. Okay, so we don't need to draw all of these. We know this is an increasing function, and since it's an increasing function, it's always going to be an underestimation because we're going to have this space that's left over. So we can say, because R of t is increasing, left Riemann sum is an under approximation, under approximates. Okay, Finally, part D. So we have the integral from 0 to b of r of t dt. And it wants to know, what does this mean? So we know that this integral is the area under the curve, right? And that area is going to have what units? It's going to be the rate in gallons per minute is the y. And then the x-axis is just minutes. So then when we find an area, it's going to be gallons per minute times minutes, which is just gallons, because minutes cancels. Okay, this comes from the fact we know that the integral of a rate function is always the net change, right? So this is going to tell us how much fuel was actually consumed. Okay, if we're integrating the rate of fuel, then this will tell us how much fuel has actually been consumed over the course of how many hours, b hours. So we are going to say, or is it minutes, sorry. Yeah, minutes. Okay, so we're going to say that this is amount of fuel consumed in gallons, make sure we have units, over b minutes of flight time. The integral of a rate function is net change. How much did our fuel consumption change over the course of the flight? How many gallons did we burn? So now if I say, what about if I throw the 1 over b out front? 1 over b integral from 0 to b of r of t dt. Okay, well, this is just going to be the average rate fuel is being consumed, because this is our average value theorem, average value formula. If we take the integral of the function and then divide by the change in the independent variable, which this would be equivalent, again, to writing integral 0 to b of r of t dt divided by b, right? B is how much time has passed. So this is going to be the average rate fuel is being consumed. Okay, this is average rate fuel was consumed over b minutes, and then it's going to be in gallons per minute. Sorry, it's getting kind of messy down here.